few lectures back, we talked about processes. Now, a process can be an independent process or a process can be a cooperating process. An independent process is one which does not affect or is not affected by other processes executing in the system. Whereas a cooperating process is one which gets affected or does affect other processes that is executing in the system. Now, designing a system in terms of cooperating processes have many advantages. For example, you can have a modular design. You can achieve speed up, especially when you assign cooperating processes, the different processes to separate processors in a multiprocessing system. You can achieve sharing of information. Now, this sharing of informations can be total in the sense that entire address space, both the data segment and the code segment is shared, as is the case of the thread, the lightweight process. Or it can be through some global variable, the shared variable that exists in some common memory or the global memory we call a shared segment. Now, in such cases, when processes do access this global data or a common file through which these processes also can communicate, then inconsistency of data may arise, especially when more than one process tries to access and update the data. Now, in these lectures, we will see what can be the pitfalls under such situation and what actions and precautions we can take so that data consistency is maintained. But before that, let us talk about concurrency. Now, so far as concurrency is concerned, we can have the real concurrency, or we can have what we call is a virtual or apparent concurrency. Okay, let us see exactly what we mean by real concurrency or what we mean by virtual or apparent concurrency. Now, suppose that we have two processes. One is, say, a rate process, another is a, say, green process. Okay. Now, these two processes have been given two separate processors, and therefore, you see these two can execute simultaneously or concurrently. Okay, this is in terms of time that I am talking, that both the rate process as well as the green process in time is progressing. Okay, I am not talking about the amount of computation, say the rate process or the green process is doing, because that will depend upon how powerful the processor on which the rate process is executing or the green process is executing. Now, this is what we call that real concurrency that is achieved in terms of a multiprocessor system. When the rate process is assigned a processor, the green process is also assigned a processor. But in the case of a single processor system, naturally these two processes cannot proceed simultaneously, and therefore what concurrency we get is that, say, first rate process goes, then it is preempted, okay, and then the green process grows, and then once more possibly the rate process comes. I am assuming only the two processes are there, and say once more the green process comes. This, what we call, is apparent or virtual concurrency. Okay, therefore this is our real concurrency, and this is what we call the virtual concurrency. Okay. Now, the problems associated with sharing of common variables are the same whether it is real concurrency or whether it is virtual concurrency. In this case, we talk about that is basically an interleaved execution. Okay. Of course, in the case of a real multiprocessing also, that interleaved execution on a particular processor can take place. Okay, but the important aspect that I would like to emphasize here is that whether it's a virtual concurrency or whether it's a real concurrency, the associated problems of sharing a common variable remains the same. Now, to highlight the problem of cooperating processes, let me take one example. This is an example of a bounded buffer producer-consumer problem. Okay. Now, this is a shared data. The program has been written in Pascal. In fact, it is written in concurrent Pascal. On the Pascal, but Pascal is a subset. I am just defining few of the terms that is necessary for explaining this program. For example, n is a variable which is of integer type. Okay, that n is in fact is the size of this buffer. I call it as a bounded buffer because the size is bounded. It's basically a producer-consumer problem, as I said. By producer-consumer problem, I mean that a producer is producing certain information which the consumer is consuming. It may be, for example, say the producer may be the producing data, and the consumer may be a writing process which is formatting the data and printing it. Similarly, a producer may be producing some information for some other process which will be consuming it, that means inputting those informations and be further processing it to be transmitted to somewhere else, possibly, or to some other process. This is a very classical problem, the producer-consumer problem. And here we are talking about the producer-consumer problem in terms of a bounded buffer, where the producer is producing an item, is putting into the buffer, and the consumer is taking that item from that buffer and consuming it. To do that, firstly the buffer has to be defined. This is, I said that n is a variable of integer type. These letters which have been written in pink, we will take them to be reserved words. That means this will not be used for any other purposes other than for which it has been meant. Okay. Here item is of some type. The type I have not defined, and it doesn't matter here also. It is Pascal-like. It doesn't mean that I am exactly using the Pascal syntax. Okay. Here that item type has to be defined. When such definitions is necessary, we will give the definition. Similarly, this buffer is a variable which is an array of n items. That array indexes can start from 0 and go up to n minus 1. That means it can start from 0, 1, 2, 3 to up to n minus 1 it can go. Okay, I am taking it to be a circular buffer. And this is an array of items, right? And the rear and front are integers which can have any value between 0 and n minus 1. That means these are the limits, okay, to which the front and rear, these two variables can achieve, can attain, okay. Now, what exactly happens is that initially the front and rear are initialized to 0. That means at this point, okay, at this 0 point. Rear points to the element which has been put last into the queue, okay. This circular buffer will be treated as a queue. That is, it is essentially a first in, first out buffer. Which comes in first will go out first. Rear always will point to the last element that has been put into the buffer, which means if another element has to be put into the buffer, the rear will be incremented and that element can be put into that buffer in that position, right? And the front will always point to that one location below from where the buffer, in the buffer the items are there. For example, here front is pointing to 2 and the elements that are there starts from the location 3. That means 3, 4, 5 and 6 these are the elements that are full, rear pointing to the last element that has been put, and front, from front we can take the amongst them the first element that was put, but incrementing the front first and taking out the data. Therefore, front will always point to a location which is one less than from where the data have started. Okay, the items are there within the buffer. Now, the two conditions have to be seen. One is that buffer full, and another is a buffer empty. Now, first let us see the buffer empty. The buffer will be empty when rear and front are the same. For initially, for example, all of them are here, both of them are here, that the buffer is empty. Okay. Now, as we go on putting the elements, rear advances, and as we take out elements, the front also advances. Now, whenever the front ultimately will catch up with the rear, that means both are the same value, naturally the buffer is empty. Therefore, the buffer empty conditions is rear is equal to the front. Okay. Now, buffer full condition is naturally when the rear is one step behind the front. For example, the rear just makes one turn across the entire circular buffer, and if it comes over to here, then you see the buffer is full. There is no more element that can be inserted into the circular buffer. Therefore, rear is one step behind the front is a situation where we say that buffer is full. Okay, that condition has been written in this reading. We say that rear plus 1 mod n. I take a mod n because it's a circular buffer. Once its rear comes over to here, it will cross over to 0 once more. Therefore, rear plus 1 mod n will be front. Okay. Now, our producer and consumer will cooperate in terms of this shared buffer. Okay, this circular buffer is a shared data which our producer process and the consumer process will cooperate. I just given here the producer process and the consumer process side by side. Okay, this producer process goes on indefinitely. That means producer process starts repeating until false, which means this will go on repeating forever. Okay. Similarly, the consumer process will also repeat until false. That means it will go on repeating forever. Now, the typical producer process will be that, let's say, produce an item in next b, where next b is a variable, naturally of the type that has been defined. Then while buffer full, do no operation. Now, if the buffer is full, then naturally producer cannot put that item into the buffer, and therefore it will do no operations, means it will go on waiting over to here. This doesn't do anything, which means while buffer is full, it is doing no operation, and therefore checking this buffer full condition continuously. It will be waiting here in a busy wait loop, okay, till it finds that buffer, there is some empty space in the buffer. When it gets an empty space in the buffer, then rear is advanced. You see, in that case, the rear is advanced fast, and the item is put over there. Okay. Then rear plus 1 mod n to take care of the circular buffer. This mod n has been given, and then the element that has been produced in next b is put into that location, in the buffer location. Okay. Therefore, this is our producer process. It goes on forever. It goes on producing one item at a time, and then it sees whether the buffer is full, and if the buffer is not full, then it puts that element into that buffer. Okay. Now let us come to the consumer process. In the case of a consumer process, here it first that whether the buffer is empty or not, because if there is buffer is empty, then naturally it cannot take out any element from the buffer, and therefore here also here is a busy wait that is there. Okay. The processor essentially is doing nothing, only waiting here till buffer empty turns out to be false. That means there is something in the buffer. Then front is advanced. You see, naturally the front has to be advanced to get the element from that buffer. Front is advanced. Modulo n is to take care of the circular buffer, and the element at the buffer front location is pushed into the next C, and then the item in the next C is consumed by the consumer. Therefore, this is our producer-consumer problem, which are cooperating processes, and they're cooperating in terms of a shared buffer, which has been shown over here. Now, that's quite fine as long as the way that we have said that the producer produces an item, then increments it, puts the element into the buffer, and this goes on continuously. Similarly, the consumer can, when consuming, increment front, take the element from the buffer, okay, and can continue with it. But there can be certain problems associated with it. Okay, let us see what can be the problem. Say, instead of that buffer, let us just put another variable here. Okay, that producer process, whatever was there, I have just added one statement that count is equal to count plus 1. That means count is incremented by 1, is pushed into the count, just to keep track of right at any moment how many elements are there in that buffer. Similarly, here the count, when consumer is taking out some element from that buffer, the count is decremented. Therefore, at any instant of time, that count should show that how many number of elements are there in that circular buffer. Now, let us examine it a little bit more closely. Now, whenever is a question of count is equal to count plus 1 is concerned and is executed, generally it will be executed this way, that count will be first taken into, say, some register 1, okay, then the register 1, say, will be incremented by 1, and then register 1 value should go into count. Therefore, 3 steps will be necessary to execute count is equal to count plus 1 instruction. Okay. Say this register 1 I am using here is R1. Similarly, okay, the register 1 that will be used by the consumer process is, say, R2. Okay. Now, what may happen is this, that because of the scheduling or because of the timing, that this entire operations of producer is done, okay, and then all the operations, for example, that register 2 count here, the count goes to register 2, then register 2 plus 1 is incremented, and then register 2 goes to the count. Okay. Now, it may so happen that, as I say, that this entire operation is over, and then this operation is done, either in real concurrency or apparent concurrency, then we will not have any problem. Okay. So, for example, either all these operations are done, and then these operations are done in terms of the time, or all these operations are done, and then these operations are done in terms of time, okay, then we will not have any problem. But think of a situation that these two processes are so scheduled that this is what happens. Okay, say producer is scheduled at that time that count is transferred to R1. The producer is still scheduled, still in the processor. Then R1 plus 1 is incremented, okay, and goes to R1. Then this producer 1 is preempted, okay, and the consumer 1, in the case of a single processor system, that it is preempted, or in the case of a multiprocessor system, the consumer starts, okay, these two operations are done by the consumer. That means counts go to R2, and R2 is decremented, okay. Then once more the producer is activated, then R1 goes to count, and then the consumer is activated, R2 goes to count in terms of our time frame as a time proceeds. This is the way the instructions are executed. That means these 6 instructions are executed in an interleaved way, as has been shown over to here. And let us see what can be the problem. You see, let this be count, okay, and let the initial value be 10, okay. Now when count goes to R1, then R1 is now containing 10, and R1 has been incremented, therefore R1 is now 11. Now here the count goes to R2, therefore R2, and you see that count is still containing 10, therefore R2 will now contain 10 also, because count has not been changed. Then R2 is decremented, therefore R2 is containing 9, okay. And then R1 goes to count by producer, that means 11 now comes to count, okay, and immediately afterwards R2 is sent to count, that means 9, oh sorry, this 9 goes to count. You see, in place of that, if, say for example, either all these instructions are executed and these 3 instructions are executed, okay, or these are executed, all these instructions are executed together, and this instructions is executed, then the count value should be same, okay, that it should retain the value 10. However, we have got a value of 9, right, and which is immediately, you can see, it's a wrong result, and that is due to the fact that all these operations, that means taking the value of the count, incrementing it in the register, and sending the value back to the count, in between other processes can get executed and can approach the shared variable count. Okay, that in fact is a problem whenever there is a shared variable and you cannot do this operation, the entire operation that has been shown here or here, as an atomic operation or as an indivisible operation. By atomic operations, I mean that starting from here to here, the entire these 3 operations will be executed as if it's a single operation, and in between no other operations is permitted on the count. Okay, that we call an atomic operations or indivisible operation. Okay, I am assuming, of course, one thing, that the load, store, etc., these operations are atomic operations, and actually in machines these operations are treated as an atomic operation. Therefore, the major problem is turning out to be that since these are not atomic operations, they can get interleaved insofar as executions is concerned, leaving a wrong result in the shared variable count. You can see, you can naturally think of other interleaving of these operations, which will make this result something different and also wrong. Okay, but naturally there can be sequences of operations of these operations. There are maybe sequences of these operations which will leave the result correct. Okay, therefore the situation as I have told, immediately demands that whenever such a situation is there, we'll have to treat them as if all these operations are indivisible, which means that atomic operation. And if we cannot achieve it, the possibility always exists that a sequence of operations of this kind will ultimately leave a wrong result in the shared data. Now let's see what we can do, okay, so that a sequence of such operations can be treated, okay, as an indivisible operation. Actually, one important thing, that one terminology I should define here, that whenever two processes are trying to access the same variable almost simultaneously, we call such a situation as a race situation. Okay, therefore all our problems comes out because a race situation exists. Now let's see, as I say, that we'll have to may have to deal a sequence of operations as an indivisible operation. What we can do about it, right? Now, what we can do is this: such a sequence of operation, okay, a segment of a program can be declared as a critical section, right? So critical section is a section where one program or process is changing the common variable, updating the common files, or writing into a shared table. Okay. If that be the situation, then such operation should be kept within the critical section, and to a critical sections there should be an entry section and exit section. The critical section's property is that if there are several processes which are doing these operations on a common data or a common file, then only one process is allowed to be there in the critical section. And once a process starts doing this operation in the critical section, it completes that entire operations that is there in that critical section, that portions of that process, before it exits the critical section. Let me repeat once more that once the processes request entry into the critical section at that entry section, once a process is allowed into a critical section, it completes that entire critical section and comes out to that exit section. When one process is in the critical section, other processes which use the same global variable or a shared file cannot enter the critical section. Okay? In that way, you see that once a process has entry into the critical section, all the operations that it performs on that in that critical sections on the shared data can be thought of as if it is an indivisible operation, and therefore that inconsistency problem, that inconsistency that may be created in the data will not be there. Okay. Now, the entire process, such process, a cooperating process, therefore can be thought of, say here I have shown that as if it is a repeat until false, that means repeating forever, divided into two sections. One is a critical section, preceded by entry section and followed by exit section, and this is the remainder of the section, and it computes the remainder of the sections, and then it comes out of the here of course it is continuing forever, and within the critical section all changes to the common shared variables are done, right? Now, few requirements have to be met so far as the critical section is concerned. These requirements are that mutual exclusion, the progress, and the bounded waiting. Okay, these are the three requirements that the design of the critical section, including that entry section and exit section, should take care. Okay, let us see what are these. One is that mutual exclusion, and it says, as I said, that if a process is executing in its critical section, then no other process can be executing in its critical section. Okay, this is called mutual exclusion and is very much needed so that two processes cannot start changing a common variable simultaneously. Okay, this is one important aspect, requirement of a critical section. The second requirement is a progress, and simply written, it means that if no process is in its critical section and some processes want to enter their critical sections, then selection of the process who will enter the critical sections amongst those processes who want to enter the critical sections cannot be postponed indefinitely. Because if this is not satisfied, and then the progress requirement is not satisfied, the processes are not progressing. Okay, therefore, this is the second requirement. And the third requirement is bounded waiting. Okay, that here also that a bound is imposed on the number of times other processes are allowed entry into the critical section after one process has made a request and the request is granted. Let me repeat in simple terms, what does it mean? The says process has requested entry into the critical section, right? There may be other processes that also made the entry, request for that entry. Then say the previous process is P1, then after P1 has made a request to enter into the critical section, and before it is granted, there will be a finite number of times the other processes are allowed into the critical sections. Otherwise you can very easily see the process P1 will starve. It will never able to proceed, okay, progress. Therefore, this is our, what we call the bounded waiting. Therefore, three requirements are there. One is that mutual exclusion, second is the progress, and third is the bounded waiting. We will try to fulfill when one tries to design a critical section. Now, so as the critical section problem is concerned, there are several solutions. There are software solutions. There are solutions which needs the support or takes the support of a special hardware features, right? First, let us see the software solutions. There's a two-process software solution. I've taken only two processes here, just to have the ideas clear. Let's first give one algorithm. We call this algorithm 1. Once more written in Pascal-like statement, okay, Pascal-like language. Here, the shared variable we have taken to be turn as 0 and 1, okay. But let me say that before I describe this process and a solution in terms of turn, let us first go back to that bounded buffer problem where we have introduced a count, okay, that count, the value of the count was inconsistent because it was not neither incremented or decremented in a critical section. What other problems can be there? Okay, I mean, just to have a very clear idea of that, why we need a critical section. You see, that was a buffer, and say that was the producer process and consumer process. Okay, now you see, the situation may be that the front has come to the rear. Okay, right? Which means now the buffer is empty. Now what happens is So producer process is right at this moment has been scheduled, and rear has been incremented. The rear has been incremented to rear plus 1. That means now rear has been incremented to 8. Okay. But the front is still here. And at that moment, say the consumer process has been scheduled. The consumer will find that rear is not equal to front, though only the rear has been advanced, but the element could not be put into this buffer. The consumer process has been terminated for that time being. I should not say terminated, has been taken off the processor, and the consumer processor started. The consumer process will find that the front is less than rear, and therefore there will be a element in the buffer. It will then increment this front and will try to take whatever is here and process it, and nothing is here, which means garbage is here. Immediately you can see that total execution of the process will turn out to be wrong. Okay, therefore a total wrong processing with the data will take place. That is why we are saying that this entire operation, that means the portion here and the portion here should be under critical section. Okay, and also this should be go into your entry section. This should go also into that entry section, so that a proper cooperation between this producer and the consumer process in terms of the shared buffer takes place. Okay. So let's come to now the software solution of this problem as we started it. Here it is the process 0, and here it's the process 1. As I said that we have kept a shared variable which is turn, which can either have a 0 value or a 1 value. That means the turn is a variable which can attain either a 0 value or a 1 value. Okay. Now all these reserved words now I have underlined. Okay, that for example variable I have taken to be a reserved word, etc. This is a process 0 and the process 1. Now once more this process 0 is executing forever. Process 1 is also executing forever. Now what it does is that the process 0 that while turn not equal to 0, it does a no operation. Okay, but if turn equal to 0, then it comes out of this and enters the critical section, executes the critical section. On exiting from that critical section, this is the exit section, it makes turn equal to 1, and then it enters the remainder section. After executing the remainder section, it continues once more. Okay. Here the process checks that while turn not equal to 1, it does no op. That means it busy waits. But if turn equal to 1, then it enters the critical section. On exiting the critical section, it makes turn equal to 0, and then it enters the remainder section, and then it executes forever. Okay. Now basically turn is a variable which can be either 0 or 1. Okay. Say initially let's this be my turn. Okay, and let the initial value be set to 0. Okay, when we started the operating processes, the process 0 and the process 1. Now here you see, since turn is equal to 0, now this will enter the critical section because this will be false, and therefore it can enter the critical section. But since turn is equal to 0, that means turn not equal to 1, it will busy wait here. Therefore turn essentially determines whether the process 0 or the process 1 enters its critical section. Okay. Turn 0 means process 0 is in critical section, and turn 1 means process 1 is in critical section. Okay. Right. Now once the process 0 enters the critical section, it executes the critical section, then it makes turn is equal to 1. That turn is now equal to 1 and it enters the remainder section. The moment turn is equal to 1, the process 1, if it was waiting here, will enter the critical section. Okay. Therefore, it enters the critical section, executes the critical section, makes turns equal to 0 when it exits it, and it is in the remainder section now. And in the meantime, possibly process 0 is once more in this intersection. It finds turns equal to 0 and then enters this critical section. Therefore, by using a variable turn, okay, that we can achieve that critical section, we can achieve that critical section and mutual exclusion. That means turn 0 means process 0 is in the critical section, turn 1 means process 1 is in the critical section. Therefore, in this situation, as you see that the requirement of mutual exclusion is satisfied, but it has some problem. Okay, first problem is this, as you see here, that entry and execution of the critical section strictly alternates between process 0 and process 1. After process 0 has entered into the critical section and exits, only then process 1 can enter it. Okay. Similarly, if after process 1 has entered and exits it, only then process 0 can enter it, and this goes on in a strictly alternate way. Then process 0, process 1, then process 0, process 1, and so on, which means that speed of computation will essentially be dependent upon, will be forced by the slower of the two processes. Okay? Whichever is slower, the speed of entire computations will be forced by that. Just think of a situation that process 1 is very fast and therefore it comes out, say, makes turns equal to 0, execute the remainder section and comes over to here. But here the process 0 is slow and therefore it's still in the remainder section. Though process 1 is ready to enter into the critical section, it cannot do so because it has made turn equal to 0. It is now process 0's turn into the critical section, and therefore the process 1 unnecessarily waits. Okay, this is therefore our progress requirement is not satisfied. And another problem is, say one of the processes breaks down. Say the process 1 has broken down here in the remainder of the section after making turn equal to 0. Then the process 0 enters the critical section, makes turn equal to 1, and the remainder section comes back possibly over to here, but can do nothing, can only wait. Okay, because it has made turn equal to 1, right? And it is now process 1's turn to enter. And if it cannot, process 1 cannot enter and make turn equal to 0, process 0 cannot enter this critical section. And therefore, the entire situation, the entire system breaks down. Okay. Therefore, though in this algorithm 1, the mutual exclusion has been achieved, it is fraught with many problems. Now, what can be the solution to these problems? We will see in the next lecture.